So let's recap what we know. If we define mu I as beta naught, then beta naught hat works out to be y bar. So if we only look at horizontal lines, the least squares estimate of the intercept is that line that's the average of the outcomes, which makes sense, right? We're disregarding x then. If we look at regression through the origin, then the line, the slope of that line works out to be that guy. What about when we have a intercept and a slope? That is, we don't restrict ourselves to horizontal lines or lines through the origins. That's when we get to real regression. Let's figure it out. Okay, so remember we need that to be equal to 0. So let's plug in beta naught and beta 1. So we're here, our mu I is equal to beta naught plus beta 1 xi, and mu I hat is just equal to beta naught hat plus beta 1 hat xi. Okay, so if we plug in, we get this equation right here, and we can pull the beta naught hat minus beta, group them together, and get that equation and that equation. Okay, and so if that guy is 0 and that guy is 0, and I'm sorry, that guy is 0, then we're set. Well, let's look at this one first. So that yields two equations, two unknowns, right? So we should be able to solve it. Okay, well, let's look at that one first. And if you solve that, if you expand the sum, we get that ny bar minus n beta naught minus n beta 1 hat x bar, and this implies that beta naught hat equals y bar minus beta 1 x bar. So now we can then plug this solution for beta naught into this other equation. Okay, and so if we to set that one equal to 0, and so here I have it rewritten down there where I've then taken my beta naught and plugged in that equation right there. Okay, let's continue on to the next page. And this has a nice simple form. It's the centered y's minus beta 1 times the centered x's, and it appears like very similar to our regression through the origin equation. So then we can solve this. We get summation yi minus y bar times xi minus beta 1 summation xi minus x bar times xi equals 0. Beta 1 is what we want to solve for. We just solve and we get this guy right here. The beta 1 is the summation of yi minus y bar times xi divided by the summation of xi minus x bar times xi. Now, let me just note that summation of yi minus y bar times x bar is equal to the average, because x bar doesn't depend on I, yi minus y bar right there. But this is the sum of the deviations around a mean. But we already know that to be 0, right? We already know when we center random variables, their resulting mean is 0. So if we were to take this xi right here and this xi right here, and the same is true whether this was yi minus y bar or xi minus x bar, we can subtract off, we can turn it into xi minus x bar instead of just xi in each case, because then if we multiply the sum through, it is equal to 0, right? That part's equal to 0. Okay, and the nice thing about that is then this quantity right here, we could divide it by both of them. We could divide it by n minus 1 in the numerator and n minus 1 in the denominator, and we haven't done anything. We've multiplied by 1. And then what we see is that this works out to be the correlation of y and x times the standard deviation of y over the standard deviation of x. And this is the sort of famous formula that the slope of the regression line is the correlation, the empirical correlation, times the ratio of the standard deviations. And then, of course, recall that the beta naught, the intercept, it works out to be y bar minus beta 1 x bar. This, by the way, guarantees that our regression line always travels through the average of the point that is x bar, y bar. Our regression line always travels through that point, which is interesting and kind of good in that we would expect it to be the case, that the line would travel through the exact middle of the data. Okay. Get that again. Okay, so the least squares model fit to the line, to that line right here. Let me see, to that line right here, through the data points xi as the outcome. It works out to be, notationally, we call it y equal beta naught hat plus beta 1 hat x, and it works out where the slope is that guy right there, and the intercept is that guy right there. Okay, and the slope has this famous formula that it's the correlation times the ratio of the standard deviations. Notice, by the way, the units work out right. So the correlation, right, that has units of y times units of x, right? And this has units of y, and this has units, I'm sorry, let me try again. The correlation is between -1 and +1 is a unit-free quantity. This guy has units of y, this guy has units of x, so the units of the slope are units of y over units of x, which makes sense, right? The slope is the change in y over the change in x, so it has to have those units. Okay, so there we go. Beta 1 has the units of y over x. Beta naught has units of y, of course. The line passes through the point x bar, y bar. You can double check that just by plugging in if you'd like. And the slope of the regression line, just if you were to reverse y and x, is set x is the outcome and y is the predictor. Well, it's pretty clear what would happen. You would wind up with the same correlation times, instead of standard deviation of y of standard deviation of x, you would multiply it times standard deviation of x over standard deviation of y. It's also neat that how important regression to the origin is. If we had simply centered our data, forced it to go through the mean of the data by centering the x's and centering the y's, and did regression to the origin, all right, got an intercept, then you get the same slope, right? Which that makes a lot of sense, right? So if we don't fix the intercept, we get a regression line that goes through the average of the y's and the average of the x's, and we get a specific slope. If you go ahead and center the data so that the origin is the means of the y's and the x's, then and do regression to the origin, then you get the same slope. Okay, that makes great sense, and of course that works out. If you normalize the data, don't just center it, but then also scale it so that it has both mean 1 and variance 1, mean 0 and variance 1, excuse me. Then your regression slope is nothing other than the correlation, right? Because the resulting centered and scaled random variables, they have slope. Then their standard deviation is 1, so the formula would work out to just be the correlation. Okay, so let's revisit Galton's data. In this case, just to not have to keep typing the $, why don't I just define y and x, and then our beta is the correlation of y and x times the standard deviation of y over standard deviation of x, and our beta naught is mean y minus beta 1 mean x, okay? And then we could spit those out, right? And just to double check myself, I'm going to grab the coefficients from the R program LM, which does exactly regression, y tilde x, and you can see, of course, that they work out, of course, to be the same. So I didn't mess up my math. Again, I wanted to illustrate that if you reverse the predictor outcome relationship, that just all you got to do is flip the standard deviations. So our beta 1 now is going to be standard deviation of x divided by standard deviation of y. Beta naught is this guy. And then here now, instead of, I'm going to compare them to the coefficients I get. Instead of y tilde x, I'm going to do x tilde y, where x is treated as the outcome, and of course they agree again. And then let me point out this last point. Regression to the origin yields an equivalent slope if you center the data first. So why don't I define y-centered as y minus the mean of y, x-centered as x minus the mean of x. I'm going to take my beta 1 as my regression through the origin slope, which, remember, regression through the origin was just summation yi times xi divided by summation xi squared, which is what that quantity is right there. And then let me get my, I'm going to compare my slope, beta 1, 0.64, and I'm going to compare it with the coefficient if I included an intercept, which again is 0.64, you see. So the regression through the origin slope, having centered the data, is exactly the same as the slope as you get if you were to fit an intercept and not demean the data first.